State University, and today he's talking about the interplay of topology and geometry and fractional quantum Hall liquids.
Well, I would like to, well, let me see. Do I need to actually turn on the mic? Maybe not. Well, I'll turn on anyway. So let me see. Oh, there we go. Yeah, my sound. Yeah, so I'd like to join the previous speakers in thanking the organizers for putting together such a wonderful conference and invite me to join. So if I'm not mistaken, I'm actually the only Floridian here who is not affiliated with USF. So that's a distinction I will not forget. I will tell the UF people about that, among others. I would actually also like to thank the previous speakers from whom I have learned a lot, and very unexpectedly, there are quite a few connections to what I'm going to talk about, which I'm going to actually refer to during the talk. So yesterday we heard a lot about fractional chain insulators, quantum spin liquids. These are topological states of matter, which started some 45 years ago from von Christian's discovery of integer quantum Hall effect, and he got his Nobel Prize 5 years later, 40 years ago now. The fractional quantum Hall effect was actually discovered only 2 years later, but they had to wait for, I don't know, 16 years to 1998 to receive their fair share of honor. So I actually came from Florida as an assistant professor, like some of the organizers here, in 1999. And when I gave talks, I would brag about these Nobel Prizes just to impress people. I'm working on very hot field important problems. But very quickly, I figured these Nobel Prizes are actually liabilities, because people start to question what possibly new can you talk about after not one, but 2 Nobel Prizes. And time went on, things got worse, because more Nobel Prizes came. So to me, the graphene Nobel Prize is also quantum Hall Nobel Prize, because the way that we got convinced of the Dirac nature of electron and graphene is because this actually, in the proper units of 4e squared of h, the integer quantum Hall sequence is actually quantized at half integer values, and the half integer shift comes from the pi Barry phase of Dirac electrons that pick up when it actually goes around a cyclotron circle. So then came, of course, still, well, disappointingly, the most recent condensed matter related Nobel Prize in 2016. In particular, the part of the share for Solis is his deep insight that the quantization of Hall conductance is really due to the fact that it's actually a topological quantum number or invariant. So since then, topology really dominated condensed matter physics, as pointed out by Ruth yesterday. But that was also recognized by people outside condensed matter physics. For example, one of my non-condensed matter colleagues pointed out to me that he could simply summarize all the condensed matter colloquia he heard in the last 20 or so years by this topological equivalence down at a coffee cup, which of course is a joke, but I also take it as a compliment. So I feel, I mean, now I'm actually one of the more senior condensed matter physicists up in Florida State. I need to find a way to actually respond to that. So I'll give my response at the end of talk, but today, I'm actually now going in the orthogonal, or in some sense, perpendicular direction of topology. So what I'm going to emphasize is actually geometry. So this started to me in 2011, some 14 years ago, now when Duncan Haldane published, to me, very important paper in which he emphasized that there's actually very interesting non-universal physics in fractional quantum liquids. The universal properties like quantization of Hall conductance come from topology, but there's also non-universal physics, some of which I'm going to discuss, which actually is associated with geometry, not just topology. So, well, Jay is not here, but I would like to make a connection with the joke that she made yesterday about her talk with AI. So, in a way, the talk today is actually about my effort to learn from this paper and the struggle in the process to translate what Duncan talks about into a language that I can understand. Now, I wish there is a machine that can actually do that, but I think I have an advantage because Duncan published so little. So there's not enough data for the machine to learn. and I still, and even have the advantage that I get to talk to him once in a while. So I think I can still beat the machine on that front, but probably not for very long. So getting to something more serious. So for the first part of my talk, I will try to convince you that this geometry that Duncan talks about is not just a theoretical construct. It's actually something real that people can actually measure and actually see in front of their eyes. So the theory has actually advanced to such an extent that you can actually make very detailed comparison between theory and experiment. So for the second part, which is the main part, I'm going to discuss actually the highly non-trivial dynamics of this geometry. Well, so this geometry has its quantum fluctuations, which gives rise to some very unusual excitations that were named gravitons because they carry spin 2, just like the quantum gravity gravitons. And again, I'll try to convince you that these gravitons can also be excited and detected experimentally. So my first idea was to use acoustic waves that act like gravitational waves, which can actually excite gravitons. That idea I still like, hasn't been realized in the lab yet, but a closely related idea has, and that is to use Raman scattering based on circularly polarized light that not only can excite these gravitons, but very importantly, can probe its chirality. And turns out we have made some specific predictions about these chiralities, and they have been confirmed experimentally. And perhaps most excitingly, we can use these chiralities to potentially pin down the topological order behind this bi-half state, which actually we still don't know for sure what the topological order actually is. So let's start nevertheless with topology. So I'm going to show actually a lot of pictures, but not a lot of topological equivalence classes, or almost no equations as a matter of fact. So from the sort of bigger viewpoint, the initial quantum Hall effect, although extremely influential, is actually trivial as far as the topological order is concerned. Basically, if you view the electrons as some dancers, like Xiaogang Wan would actually like to make the analogy of everybody just doing her own dance under, of course, the constraints. One is that lambda quantization, so each loop has to enclose one flux quantum if you are in the lowest lambda level, but also Pauli exclusion principle, basically everybody has to dance in her own loop and not step on the neighbor's territory. Now the Laplace dancing pattern, which got this share of the Nobel Prize, is much more interesting. So there, you actually have more freedom because there are fewer electrons, the freedom factor is smaller. So there's more room. So in addition to satisfy these hard constraints, you can actually get something more, if you wish, optional but luxurious, which is try to lower the interaction energy. So you want to actually stay away from each other because these are charged particles with one over Coulomb interaction. And the way to ensure that in the lowest lambda level is if you have one dancer here, another dancer cannot get too close. And to do that, you enforce the constraint that a second dancer has to dance around the first dancer in a loop that encloses 3 flux quanta. So this is my pictorial way to explain the Laplace topological order. So there's actually even more exotic topological order, which I call the Maury dancing pattern, which gives rise to even more exotic fractional quantum Hall states like non-abelian state. I'll actually get back to this at the very end of the talk. So what is the geometrical aspect of this dancing pattern? Well, so turns out this constraint of 3 flux quanta is actually not completely rigid. It does not completely determine the shape of the circle. You can actually distort it, for example, to an ellipse, such that it's more elongated in the x direction, but therefore squeezed in the y direction. Well, why would you actually want to do that? Well, there are at least 2 reasons that I can think of. The first is somehow in your crystal, there's an anisotropic dielectric function, so that the Coulomb repulsion is actually stronger along the x direction. So you would like to stay even more far apart, but at the expense of actually allowing electrons to come closer together. So another is anisotropic band structure, in which case the electrons naturally would like to dance not in a circle, but in an ellipse. So in that case, it would naturally like to actually do this distortion. So these are not exactly Duncan's words. Okay, so I'll show my translation, some of them at least. So he pointed out that, well, this dancing pattern actually has both topological and geometrical aspects. The latter is actually determined not by topology, but actually by energetics. It's actually sensitive. That's why it's non-universal. It's sensitive to the specifics of the universe, the electron-electron interaction, and in particular the effective mass anisotropy. So he used this term, which probably has been used by mathematicians way before, namely area preserving diffeomorphism, namely that you can change the geometry, but with some constraint, namely that the geometry change cannot change the area. So basically, this is distorted circle to ellipse. Okay, so what immediate consequence of this observation is, unlike what you may have heard, namely, well, we have a lot of computational physicists here. We do a lot of variational calculation, but to get a Nobel Prize, you have to write down a variational wave function that you don't have to do any variation. There's no variational parameter for the Laplace wave function. Well, that turns out not to be exactly true. There is actually a hidden variational parameter in the Laplace wave function or Laplace states more generally, which is this geometrical parameter. We actually, shortly after Duncan pointed this out, explicitly constructed this family of Laplace states. So the original Laplace wave function is a very special member, which is completely isotropic. So this is the threefold node. But if you actually distort it, well, the circle becomes more or less like an ellipse, and this one node for Liang, threefold node becomes three separate nodes. Okay, so this is with a particular anisotropic parameter. The parameterization is not so important for my discussion. But the problem is experiment cannot distinguish between these two. All what you see is this plateau and the fact that ρSS goes to 0. So in this sense, topology is a bad thing because it hides a lot of interesting details. Okay, so there's no way from the experimental data to tell whether it's this state or that state or any state in between that's actually realized in that particular sample. So how are you going to reveal and measure this geometry? Well, it turns out the answer is to get rid of the topology. Well, how do you do that? So 1/3, of course, is not the only fractional quantum Hall state. So there is a whole sequence, 2/5, 3/7, etc. And there's actually a particle conjugate sequence, which actually ends up at 1/2, which is actually not a quantum Hall state. But in some ways of understanding fractional quantum Hall sequence, you can actually view the 1/2 state as the parent of all the neighboring quantum Hall states. So if they carry this geometrical character, so should this parent state. So the idea, therefore, is to probe the possible existence of geometry as this 1/2 state. Well, it turns out the 1/2 state is extremely interesting, which I don't need to explain to this audience in its own right, even though it's not a quantum Hall state. So this is believed to be a composite fermion from a liquid state. And the way to understand that is, well, filling is 1/2. So there's one electron for every 2 flux quanta, but you can pretend that flux quanta are actually carried by the electrons themselves, or you can squeeze the flux quanta onto the electrons. So that actually gives you a composite object, which is still a fermion, known as composite fermion, very creative name. So they also form a Fermi surface. So there's a lot of experimental study and evidence for that. But not that long ago, Mansell-Shagan's group asked a to me, very interesting question, which is, well, if we start with the electrons at 0 magnetic field, obviously they form a Fermi surface. And if you have isotropic effective mass, the Fermi surface is singular. Circular. But, well, by symmetry, composite fermion Fermi surface would also be circular. If there is effective mass anisotropy that makes the electron Fermi surface anisotropic. Well, what happens to the composite fermion surface in this case when you turn on magnetic field? So they did actually detailed experimental studies. So there are 2 different ways to control the anisotropy. One is to actually apply in-plane magnetic field. We usually use the in-plane field to actually change the Zeeman. but it actually also has the orbital effect, which impacts the electron dispersion. And the other is to actually just directly use string to distort the lattice. And I'm not going to go into the experimental details of how you measure the Fermi surface. That's, of course, a bread and butter type of probe in condensed matter physics. But a surprising finding is the following. So in the most naive mean field theory, the effective mass anisotropy for composite fermion is actually the same as the electron. Basically, you just spread out the flux and you get back to the electrons. And theoretical papers have been written predicting that, well, the anisotropy should be exactly the same. But what Mansour Group found is that, well, not surprisingly, the composite fermion is anisotropic if the electron is anisotropic, but the composite fermion surface anisotropy is always less than that of the electron, and usually often much less. So that was a puzzle, and the relation between the two is not clear. So here comes my first claim and first translation. So I claim that the composite fermion Fermi surface is actually a direct reflection of Helmholtz geometry. And now I can actually translate this, to me at the time at least, unfamiliar term, area preserving diffeomorphism, to a much more familiar term in condensed matter physics, and that is known as Luttinger's theorem, which says the shape of the Fermi surface can change, but its area or volume, well, in 2D, volume is area, cannot change. Now, you might be a little bit surprised because I was talking about the real space geometry earlier, but this is all of a sudden momentum space geometry because I'm talking about Fermi surface. But remember, we are talking about what happens in a strong magnetic field. In a strong magnetic field, the real space and the momentum space are actually dual to each other. It's really a 90-degree rotated version of each other. Because if you remember, in your first quantum mechanics course, solving the Landau problem, you probably use the Landau gauge. So the wave function is the momentum, let's say along the y direction, but what that tells you is where the wave function is located along the x. So they're actually the same thing, okay? But at least now I can use a, to me, more comfortable and familiar term, Luttinger's theorem, to understand this area preserving diffeomorphism. So now let me actually justify this statement. So this is justified by introducing an exactly solvable model, okay? So usually when we study states, we project to a given lambda level, and of course, Liang has advanced a new method based on AI that we don't have to do that now, but I'm still old school, so let's actually do that. So that allows us to completely forget about the kinetic energy, and we only need to worry about the two-body interaction, well, for electrons cooler. So in quantum mechanics, if you are given a homework problem or exam problem where there's no kinetic energy, but only potential energy, well, it must be a Christmas, right? Because quantum mechanics is hard because kinetic energy and potential energy don't commute with each other. But of course, there's no free lunch. Well, unless you come to this conference. Because you have to actually project this two-body interaction onto the particular lambda level you are in, usually the lowest lambda level. And during the projection, you have to replace the position of the electron by guiding center coordinates, which actually don't commute with each other. The x and y components don't commute with each other. So we are actually dealing with a non-commutative space in van Hall effect. And the band structure information is actually encoded in the form factor of the lambda level. For the lowest lambda level, the form factor is a Gaussian, just reflecting the fact that the lowest lambda level wave function are Gaussian wave function. Lowest lambda level is the same as a harmonic oscillator. And the anisotropy of the band structural effective mass is actually encoded in the anisotropy of this Gaussian form factor. Okay? So now the exactly soluble model is the Gaussian model. So the nice thing about Gaussian is it's Fourier transform, which is what enters the Hamiltonian, is also a Gaussian. So let's assume the Coulomb interaction, well, in this case, a Gaussian interaction is isotropic. So once I do the Fourier transform, I get an isotropic Gaussian. So what I need to do now is to combine this isotropic Gaussian with this anisotropic Gaussian. So I get yet another Gaussian with the anisotropy that is somewhere between one being complete, meaning complete isotropic, and this A, which is the anisotropy of the band structure. So as a result, you get a anisotropy that's somewhere between 1, the isotropic limit, and the actual band structure anisotropy. But I have not told you what filling factor I'm in now, because this is just a property of the Hamiltonian itself. So if I populate the lambda level with half filling, I get a HAR-like composite Fermi Fermi liquid state. So this would show up as a Fermi surface anisotropy. But with the same model, if I populated with 1/3 filling, I get the Laplace state with a anisotropic one. And therefore, the two have exactly the same anisotropy. So this is of course a exact result, but for a specific model. But it's already qualitatively in agreement with experiments and has been, not surprisingly, numerically confirmed. So partly motivated by the theoretical advance, the Shagan group performed a more detailed study, previously using in-plane field, now using string, the dependence of the composite fermion anisotropy and the electron anisotropy, which they call RF, alpha F being fermion. And they found this empirical dependence that the composite fermion anisotropy seems to be the square root of the fermion anisotropy. So I actually didn't realize it myself, but they tried to fit it to the formula that I actually showed in the previous slide. I found that if you factor out this square root, the remaining factor involves 2 length scales. One is magnetic length, naturally, and the other is this range of the Gaussian model that I used. And if you choose the range of the Gaussian to be exactly the magnetic length, this factor actually disappears, and you get exactly the square root behavior. Now, this sounds a little ad hoc because the actual Coulomb interaction is not the Gaussian. But I already pointed out in my paper that for Coulomb interaction, it has no range if it's an infinitely thin plane. But because of finite well width, there is actually additional extrinsic length scale associated with the well width, which actually happens to be somewhere between 100 to 200 angstrom, very much, very close to the magnetic length at 10 Tesla. So this choice is actually not totally unreasonable. So I think it's fair to say that we have both good qualitative and perhaps even quantitative understanding of this geometry, at least at a static level. So what about the dynamics? So people have pointed out from different perspectives, okay, going all the way actually to Deng Hai Li and Xu Chen Zhang. There are too many Lis and too many Zhangs. This is constrained, so I need to specify who they are. In 1990, that in the long wavelength limit, the neutral collective modes of fractional quantum liquids is actually polypolar mode. And more recently, I think for good reason, some people may complain, but if you do, I'll respond. Because of the spin-2 nature, call them gravity. Okay. So the question is now, similarly, how do we actually excite these gravitons and detect them? So this actually goes back to something Liang was talking about. So normally we use photons or electromagnetic wave light to actually probe condensed matter systems. But here, due to the Coulomb theorem, in the long wavelength limit, the spectral weight is actually exhausted by the cyclotron mode. So you cannot probe or excite any intra-lambda level excitation. So Liang's way of actually getting around it is to actually break Coulomb theorem by breaking translation symmetry. There I see a little bit of issue because now you mix also the long wavelength modes with finite wavelength modes. So my proposal is in a very different direction. So another way to understand Coulomb theorem is, well, light is made of photons. Photons have spin 1. But here, now we understand we have these graviton excitations with spin 2. So the selection rule basically says that you cannot excite a spin 2 excitation with a single spin 1 particle. So that's why you cannot use the electromagnetic wave to excite them, at least in the, well, I'm going to get back to that. So what's the other options? So well, my proposal was to use gravitational waves, which is a very natural idea, right? Except when I made this proposal, this was actually almost 10 years ago. It was in August of 2015, and you might remember. Well, show me should. the very first LIGO signal came in September 2015, and it was published in January 2016. And as a result, my paper was immediately rejected by PR. So I should have waited maybe some 6 months. Anyway, well, okay, you are in the audience, so that's my opportunity to complain. You have to pay. Of course, I was not really talking about it. Backpedal a little bit, not really talking about the
But you need to
LIGO.
get to finite Q, don't you?
What?
You need to get to finite Q to get to bottom of the rotor. You
No,
need-
no. So that was the old idea. Now we claim just stay. Okay, Raman is coming. Okay, so we don't need to go to finite Q. I claim. Okay.
But at Q equals 0, it's over that.
It's not. That's the surprise. It's not over there.
So the continuum has different symmetry and they interact.
Yeah, even though it's continuum, it's not over there. That's a surprise. Okay, you're ahead. So yeah. Okay, just hold on for a few minutes. Okay, I was actually not thinking about the LIGO gravitational wave, but some condensed matter analog of gravitational wave. I didn't explain, but so as I said, the geometry is controlled by the effective mass, which is a rank 2 tensor, just like the metric tensor. So therefore, I write it as a metric tensor. Well, what is the gravitational wave that's propagating through the room? That's just some oscillation of the metric tensor. Well, so I can mimic that by making the the effective mass tensor oscillate. Well, how do we do that? Well, statically, you just add a static string. You distort the lattice, but dynamically, you just propagate some acoustic wave, which is some oscillating thing, induces some oscillated string. So you can actually generate an oscillating metric by propagating acoustic waves through the system. So I don't think it's necessary for me to go through the derivation, which is actually not so different from the previous derivation about the exactly soluble model. But the bottom line is that this string and its oscillation couples to 2DAG through a D wave operator. So therefore, it only couples to. Are we going 5 minutes? Yeah.
2 minutes.
Oh, okay. Yeah, I think that's enough time. Yeah. It actually only couples to a D wave, spin 2 excitations. So so therefore the absorption rate of this actually tells you the graviton energy. So basically, this is like doing the acoustic wave version of cyclotron resonance. So the prediction is that you should see a resonance peak out of the graviton energy. Okay. So we calculated it basically for the purpose of rebutting the rejection of PRL. It didn't succeed. We see these peaks, didn't publish it, but others did. The reason, part of the reason that we didn't publish it is because there is actually one very important property, which is the chirality, that's not revealed by that spectral function because it's dx squared minus y squared. So plus 2 and minus 2 come with this equal weight. But we end up calculating the chiral version of this, which couples to plus 2 and minus 2 separately. So it turns out for the Laplace state, you only get the minus 2. Plus 2 is actually exactly 0 for the ideal Hamiltonian. And so the conclusion of this calculation, therefore, is that the graviton not only has spin 2, it actually has a definite chirality, which is minus 2 for the Laplace state. Okay, so the proposal, therefore, to prove that is to use circularly polarized wave, very much like what Gershon was talking about. And because of the short of time, let me just say that, well, this was enough to show me, maybe while the rest of the editorial team, and we finally got a PRL out of it. And despite the editor's suggestion, in this case, the editor, I think, is show me, the paper got almost no attention for some 5 years, so can very much relate to Jonathan's joke yesterday. Except we got a little bit luckier because someone did take the editor's suggestion more seriously and published a paper with almost the same title, just adding evidence for in front of chiral graviton modes in the fractional Panova liquids. So let me just very quickly point out that exactly the same experiment, circularly polarized wave. Yeah. The only combination that couples to minus 2 shows a resonance peak. So it's not over there. I claim. Okay, well, at least that's the claim of the.
Well, but this peak, Aaron saw this peak in 93, right?
But
That's the Buckley price.
no, but well, with a different interpretation, I understand that. Okay,
Right, but it's the same peak, he didn't do polarized round.
He used unpolarized light.
He didn't polarize, yeah, I
he
was
couldn't
telling him
use
polarized.
the toroidal, which is extremely important here. Okay.
Sure.
So
Well-
so anyway, so we could discuss that, but it got a lot of media attention. So 2 days after the publication, Chinese Daily claims that the graphite was observed for the first time by Chinese scientists because experiments were done in Nanjing University. Okay. There's also coverage in Western media. I gave 2 examples: Cosmos and Earth.com, which covers Earth and Heaven respectively. There's actually in-depth discussion in more serious journals like New Scientist, how they got access to the paper, because unlike what you talked about, this paper was actually never put on the archive. So I only saw it a week before its publication because they contacted me for comments. Anyway, so I even contributed to it by writing a united commentary. Anyway, so I'm sure I'm out of time. So just now the punchline: why -2? So this goes back to topology. So the Laughlin dancing pattern, a more accurate way of describing it is that if you look at a pair of electrons, there's a minimum relative angular momentum of 3. A graviton, which of course is the excitation that's not present in the Laughlin ground state, is basically turning such a pair from angular momentum 3 to angular momentum 1. So 1 minus 3 is -2. That's where the -2 comes from. And that's simple. And therefore, immediate consequence is that if you reverse the chirality by going from 1/3 to 2/3, which is the whole state, everything reverse. So that's like flipping your sample upside down. You get +2, and that's also experimentally seen. So it looks like I have to maybe skip the most exciting slide, but you guys can ask me about it because this is really leading to something possibly fundamentally new. But let me go to the summary, and we can come back to this. So while there's still life beyond topology, and my response to my colleague now is that in addition to coffee and donut, we also have wine and beef. Well, we had beef, but not wine last night. Not complaining about that. Anyway, so some specific results, and if you want, you can use this to study quantum gravity, in which we know everything all the way down to the Planck length, because to us, Planck length is the magnetic length. Okay, thank you very much.
Time for one question.
Oh, only one question? All right, so your proposal,
Yeah,
microwave, right?
microwave.
Modulate with microwave. Acoustically.
Okay, yeah.
Acoustic wave,
Yeah.
right? So that experiment was done, obviously. There is a Nature paper by Van Klitzing and Kukushkin.
No, I'm not sure I'm talking about the same experiment, but go ahead.
Yeah, right. And there is a comment on that paper written by Steve Simon.
Yeah.
Right, basically saying that, well, guys, at Q equals 0, you can't see.
Well,
right? And it comes back to, yes, I mean, the mode is there and they didn't discover it. Aaron discovered it in 93. Now,
okay.
Phil Platzman was asking why it's there.
Well, because it's graviton. So then
No,
I agree with you.
everybody understood it's graviton. But
Okay.
why?
It took me 10 years. Okay, I only understood it very, very recently, but maybe you understood it.
No, not me. I mean, Phil and all. But do you understand why doesn't it decay? That's the question.
Well, it does decay. I mean, okay, so some controversial.
It's in the continuum, and continuum has the same symmetry.
Okay, so it does decay. So let's say numerically. There's a finite width, and of course, experimentally, there's a finite width. There's a finite width because it's a continuum. But one can cook up models in which it's not in the continuum. So there, it won't decay. But in reality, it does decay, yeah. But it's not overdamped. It's not overdamped.
Well, but the mode is at energy where the rotor has a minimum, which is at finite Q.
No. So this is the disagreement with the previous interpretation. The previous interpretation is that what Aaron saw in 93
Right.
is a pair of these. Now the interpretation has changed. Now the interpretation is that it is a mode by itself.
Well, second, the pair would have a different symmetry.
What?
Pair would have a different symmetry.
Okay, yeah, okay, but that's enough details that we probably should discuss offline. Yeah.
We go to the next one, sorry.
Okay, yeah. Sorry about that. Yeah.